and I really do not feel Welcome back to ECE 207, second day. What I wanted to announce was that your passports are due today. Those could be handed in physically up front, or they could be submitted through the drop box. Either one is fine. Homework number 1 will be uploaded on to D2L shortly. Obviously not in the next 75 minutes, but maybe sometime shortly thereafter. It will be covering homework number 1 material. Today what I hope to cover is material from homework 1 and 2, or from chapters 1 and 2. Did I say it was in homework 1 material? It needs to be chapter 1 material as homework 1. This will not lie, I guess, when we go and listen to it. Today what I want to do is go through some examples on Kirchhoffs Current Law, Kirchhoffs Voltage Law. I may just abbreviate those as KCL and KVL. We'll talk about the different kinds of sources. Obviously, we'll just deal probably with one resistor type, but those are 2 different categories of circuit elements. Then we'll start putting all of those pieces together and analyzing circuits using the tools of KCL, KVL, and Ohm's Law. Learn how to use all 3 of those in combination. And then we'll start with resistive circuits, which is another way of analyzing just circuits involving resistors. We haven't gotten any more complicated than that in chapters 1 and 2. If you came late, you missed the show and tell. I'll see if I can maybe do a little YouTube video. No, I don't know what we'll do, but maybe I'll show you a little bit of a video on the LED driver circuit and what happens when you change out the resistor to make it various levels or magnitudes. Increasing the resistance will obviously reduce the current flowing and make the LED less bright. You drop in a lower valued resistor, that will allow the current to grow or be larger, and that will cause the LED to be brighter. Let's start with what we said we were going to do today, which is KCL and KVL. KCL, as I've written in the goals section, is Kirchhoffs Current Law. Written in an equation form or with formulas, that's looking at a bunch of currents, I sub j, j being an index on different currents, and j might range from 1 up to some number, capital N might be 2, it might be 3. These are all currents coming into a particular node. The algebraic sum of those currents needs to equal 0. Really what Kirchhoffs current law says is that you cannot have charge accumulate at a node, or we cannot accumulate charge at a point, which is really what we call a node. And what we mean by a point is not physically necessarily a point, it's an electrical point. Meaning if I have just a wire from this point here, A, so if you're listening to this, you'll have to use your imagination. I'm now walking 10 steps over, and here's another point B, and if that's an electrical connection with just a bare wire, that's the same node, and it would be what we would call the same electrical point. It's physically not the same point, obviously, but electrically it is. And that's what we mean by an electrical point or a node. In words, what we're saying is that the algebraic sum of currents into or out of a node is 0. Let's, with some examples, try to get us comfortable with this concept of node, or what is a node. In this case, hopefully it's fairly clear that this connection point, electrical connection point, is a node. If that's a node, then the algebraic sum of those currents needs to sum to 0. Or you can think of it many different ways. You could say, oh, all the currents coming into that node must sum to 0. The way that I've sketched this, all of the currents are defined coming into the node, which means then in this particular case, KCL simply says that I1 plus I2 plus I sub 3 must equal 0. Which means that maybe one of those currents actually might be negative, but that doesn't matter. The signs will take care of themselves as long as we live with the definitions that we've defined. In this case, I've maybe arbitrarily selected all of those currents to be flowing towards that node. Another example. How many nodes do I have in that particular schematic? Take out your clickers and respond, and I'll be sure and record your answer. Just teasing. I heard 2. I heard 1. Any other votes? -1? Okay, now we're being silly, aren't we? Which is okay to be silly, as long as we're serious on the exams and the final. Okay? Or the homeworks even. There's really just one electrical node. I've drawn a dot to indicate there's a connection, but that's just a wire, bare wire, between those two dots, red dots, and those are electrically the same point. And because of that, charge cannot accumulate in that node, meaning the algebraic sum of those currents has to be 0. And there's a lot of different ways that you could write the relationship among those currents in this particular case, but they all should be equivalent. KCL, if we say, okay, the sum of the currents coming in must equal the sum of the currents going out. And you could say, okay, I1 and I3 look like they're going into the node. I2 and I4 are going out. With that thinking, we have I1 plus I3 is equal to I sub 2 plus I sub 4. Or you could algebraically move all of those to one side of the equation after writing this, or you could simply say, I'm going to sum all of the currents going in to that node and let those be equal to 0. Well, I1 goes in, I2 is actually going out, so it's going in with a negative sign. Does that make sense? We now have minus I2. I3 is defined to be physically, or as we've sketched it, going into the node. I4 is leaving the node, meaning a minus I4 would go into the node. And hopefully you can see that algebraically those two relationships are the same or equivalent. That's KCL. Not that hard. Let's work with KVL. Which is Kirchhoffs voltage law. KCL was we can't accumulate charge at a point. This is basically a conservation of energy type condition. This is based on energy conservation, and we'll try to talk about that in a minute, but we can't create or destroy energy. What's that? Is that a law? Thermodynamics. That's where you guys are comfortable. Maybe, maybe not. If you are, good. If you're not, fine. We'll use whichever way you like to think about it. Let's draw another circuit. This circuit has a voltage source. And with the straight bars, that usually means a DC, direct current, or a constant voltage source. If I were to draw a circle with maybe a tilde in it, that might mean a time-varying voltage source. But we'll get into that in a minute. Let's call this V1. And as I said last time, I think I said last time, the long bars are associated with the positive terminal and the small bar the negative. This is a resistor. Let's call that V sub 2. Let's call this resistor voltage drop V sub 3. It really doesn't matter how I label those per se, but if I'm going to now label my current to go in this direction, that's usually the more consistent combination of current direction and polarity labels on the different resistors. And let's just say that I have power 1 for that element. I have power associated with that resistor, and I have a third power, P sub 3, associated with that resistor. First law of thermodynamics says I can't create or destroy energy. In this case, if we take the time derivative of that energy relationship, we'll have power, which says if that's P1, P2, and P3, those must sum to equal 0 by energy conservation. We have P1 plus P2 plus P sub 3 equaling 0. Now we need to find what those are. Let's start with the easy ones, which are the powers associated with the resistors. We are going to be using, in this course, the passive sign convention. Which means that if we have a current flowing into the positive terminal, that's going to be a positive power. If the way that we've labeled the current, if that current label is going into the positive terminal, and you're going to go, well, the current could be going left or right, and it's still going into the positive terminal. The shorthand description that I'm meaning when I say into is that the current goes or touches the positive sign before it goes through the element itself. Does that make sense? If I say current's entering the positive terminal, that means that it's touching the positive terminal that we've labeled before it goes through that particular element. In this case, then, our power is plus, whoops, I'm wanting to do voltage, and I thought I learned last time not to do the eraser, but what is power from last time? Voltage times current, isn't it? In this case, then, we've already labeled the voltage as V sub 2, and the current flowing through that is I. And because of the passive sign convention and the fact that the current is going into the positive terminal, that's going to be a positive power. P sub 2 is V sub 2I. P sub 3, is it clear that that's the same relationship as P sub 2? I is going into the positive terminal of that second resistor, or the resistor with the labeling of V sub 3. With that convention, what's P1? You can think of this a couple of different ways. If you look at how I is traveling around that circuit, it's going to go into the negative sign before it enters the element, the source element. And that's different than what we just had. Or you could say, oh, I is coming out of the positive terminal. Either way, this now is associated with a negative power. And a negative power just means it's not being absorbed, it's actually delivering power to the rest of the circuit. And in this case, it's V1 times I with a minus sign. Power is delivered there and it's absorbed with the positive notation. That's the passive sign convention. We have a relationship for the P's, the powers. By energy conservation, those have to sum to 0. And we now have formulas for the powers, P1, P2, P3. Let's replace those into the earlier equation, and we now have minus V1I plus V sub 2I plus V sub 3I equals 0. We have something in common with those three terms, and that's the current. The reason they are in, or it's common, is because those particular elements are actually in series. We'll learn more about that in Chapter 2. But the same current is flowing through all three of those circuit elements. That indicates that they are in series. We can actually assume that I, for a non-trivial case, is something other than 0, and we can divide it out. We can divide both sides by that I, and doing that allows us to conclude the relationship that we're really after, which is what we'll just use now. From now on out, we'll just use KVL. We won't go through all of this, but now we've tried to verify this for a very simple case, that the algebraic sum of the voltages around a mesh or around a loop sum to 0. And if you go back, so now we're saying minus V1 plus V2 plus V3 is equal to 0. How would we get that automatically or more quickly? If we are walking around this particular circuit or loop, starting in the lower left-hand corner, we now enter the negative terminal of V1 first. There's our minus sign. That's another way to apply the passive sign convention. Now KVL, we could simply say, oh, we have minus V1 plus V2 plus V3, and now we're back to where we started, so those all have to sum to 0. And we will then conclude or write down essentially this relationship and not go through that derivation of powers again. We'll just say, oh, by KVL minus V1 plus V2 plus V3 equals 0. Let's look at another example. Maybe I should ask if there are questions, but I think this is fairly straightforward. Let's draw another circuit. Suppose we're given that circuit. That's actually an all-resistive circuit. That's Chapter 2, sort of, but we are learning KVL. In that sense, it's Chapter 1 material. How many elements do we have? We have 5 different elements. 4 are the same type of element. They may be different values. We haven't labeled those. We're not interested in that just yet. But we should have 5 different voltages, 1 voltage associated with each element. And in this case, let's just label those. Suppose we start at the left and say this is V1, plus to minus from top to bottom. The next resistor, as we move to the right, let's call that V sub 2. Let's initially go down and say that resistor, the vertical resistor, is V sub 3. Let's say the next resistor after the vertical resistor and up top on the right, let's say that's V sub 4 from left to right, positive to negative. And now, because of what we know maybe we will encounter when we go around the loop, let's just label V sub 5 plus to minus from right to left. We wouldn't have had to, but if we need to call V sub 5 something, I'm just going to arbitrarily assign that voltage orientation or label to that particular element. What can we do? Or, in analyzing these circuits, we're really looking for relationships. And we have maybe several different relationships in this particular case or this circuit. Let me draw some potential loops that we could go around. We could go around this loop, and I'll say that's loop or mesh 1. That's actually not going to give us all the information we need necessarily to solve this equation or this problem. Let's look at the other mesh or window or loop. Let's call that 2. That's really all we need, but we don't necessarily have to always do the loops in that manner. We could also say, oh, let's get silly. I said that was okay, so maybe you could even do that on the exam. But these 3 loops are not all independent of each other. There's some dependencies now among the loops. But that's okay. We're just writing KVLs for now and just trying to get comfortable with that process. But maybe I should state that we're just doing this for more practice with KVL. Whoa. If you had your head buried, good. But now we want all 3, I'm wanting you to realize that all 3 of these loops are not independent of each other. What's the relationship between the voltages that we've labeled and loop or mesh 1? Maybe I shouldn't have written that sentence. Now I have to scroll up. But let's look at it for a minute and see if you can then write KVL for mesh 1. What would you do? We have minus V1 plus V2 plus V3 equals 0. Is that what was said? For mesh 1, we have minus V1 plus V2 plus V3 equaling 0. That's one equation, or one relationship among those voltages that we've labeled. What about mesh 2? If we start where my arrow seems to begin, which is in the middle on the right side of V sub 3, we're going to go through V sub 3 first. But we're going through V sub 3 in which terminal first? The negative. So in this equation, we're going to have minus V sub 3 plus V4 plus V5 equaling 0. It doesn't matter that we've already used plus V3 in the earlier equation. We now just look at it differently and we say minus V3 plus V4 plus V5 equals 0. And that's a valid relationship among those voltages. Questions on that? Are we clear where that came from? Now let's look at the third loop or mesh. With this big loop, we're going to go through V1 through the negative terminal first. We have minus V1 plus V2 plus V4 plus V5 equals 0. And that's a valid relationship also. Questions on that? You're now experts on KCL and KVL. Yay! Give yourself a hand, right? Good. Okay. At least you're awake, following along or listening, hearing. Let's move into circuit elements and just remind us or inform us of all the different kinds of sources that we could have in our walk through ECE 207. We have two different types of sources. We could have a voltage source or we could have a current source. I did not draw that shape. See? Once we have those two types of sources identified, one or the other, or we could have both types of sources in the same circuit, now we could have independent voltage source, or we could have a dependent voltage source. And we could have the same breakdown in the currents. We could have independent current sources or dependent current sources. Typically, we write these different ways or label these differently. An independent voltage source might look like that. A dependent voltage source could look like a couple of things, but it's going to look like a diamond for both cases. This one is, let's say it's dependent on voltage, which means that maybe it has a polarity plus to minus from top to bottom, but it's now some multiplying factor, K1, times a voltage V sub x. It's dependent on a voltage V sub x somewhere else in the circuit. That's what that means. Another dependent voltage source could depend on a current flowing somewhere in the circuit, somewhere else in the circuit. It might be again labeled plus to minus from top to bottom, but now it might be K sub 2, let's say I sub y, where I sub y is a current flowing somewhere else in the circuit. And depending on what that current is, that's going to influence or determine what the voltage is of that source, that dependent source. It's dependent on another variable, and in that case it's dependent on a current. Likewise, for the current sources, we could have an independent current source, that's supposed to be a circle, and it might be labeled with, let's say, I sub s of t. And the dependent current sources are also diamonds, but now they have this current flowing through them. This one, let's say, is dependent on a voltage. This one on a current. And I think you can guess what these will look like. This is now K sub 3 times, let's say, V sub z, and this current, dependent current source that's dependent on a current, let's say, is K sub 4 I sub w. Those are the kinds of sources we will be dealing with in this class. And you'll need to be comfortable working with those kinds of sources. Now with resistors, that's another circuit element, and these are the two circuit elements, or two different types. We'll be working with sources and resistors the first week or so of the semester to try to get comfortable with these notions of KCL, KVL, and Ohm's law. And then we'll just advance to more and more interesting combinations and more different types of elements. We'll introduce some inductors and capacitors, and then we'll go from there. For now, let's look at a resistor as this rough up and down line. We'll label it R. We'll say the current going into that resistor is I sub R, and the voltage drop we will label as V sub R. Our current voltage relationship, which you should remember from now until the end of, well, I was going to say until the final, and I probably messed up last time in saying what you needed this course for. Some of you actually need this course for subsequent classes to do maybe design with filters, and we'll try to get you some background on filters so that if you're interfacing with a transducer, or let's say which might be a thermocouple, then you'll know how to filter that signal and get it into the computer. That's something that you may want to take out of this class. This is the current voltage relationship for a resistor. V is equal to Ri, or V is equal to IR. You'll need to remember that. Or you could say R is this ratio of voltage to current. We know what voltage is, or volts. That's the unit of measurement for voltage. Current, the unit of measurement is amps or amperes. Resistance is then the units is volt amperes, or this capital omega, or ohms. And we could solve for current if we wanted to and say I sub r of t is now 1 over r v sub r of t. And sometimes you might see 1 over r as another variable, which is G, and that's not resistance, but conductance, which is the reciprocal of resistance. And G is then I over V, or amps over volts. That's conductance, G, or it's the inverse of ohms, which is just the mirror image or the upside down of capital omega. And sometimes you'll hear that called mhos. Instead of ohms, it's ohms backward, mhos. Or you might hear it more commonly referred to as Siemens and given the value S for units. We'll be dealing mostly with resistance in ohms, and you won't have to really worry about the reciprocal relationships necessarily. Hopefully now, after the couple of lectures that we have, you know the relationship for power in a resistor. And if you don't, we can actually derive it. We know that power for any element is V times I. In our case, we have V sub r of t and I sub r of t. And we can now write the power of a resistor in terms of either currents and resistance or voltage and resistance. Suppose we get rid of the voltage, which we know is R, I sub r of t, and that's times I sub r of t. Or you may hear somebody say, oh, you have power loss in your resistor. Well, that's I squared R, or R times I sub r squared of t, and that's watts. Which, if you have a toaster, you probably just have a heating element in that to brown your toast or to make your toast a little darker. And we've agreed that that's roughly 1 kilowatt. So if you know now how much current you're drawing from that toaster, you can figure out the resistance of that heating element from this relationship. P is equal to I squared R. Or you may know the voltage across that resistor, and you don't want to break your circuit or tear it apart to try to measure current. Current's flowing through, voltage is across. You can measure things across that resistor maybe more easily than you can measure, pull out the wires and put your meter in between to measure current. Which means we need to get rid of the current, which is V sub r of t over r. And we now have V squared over r for the power of a resistor. Questions on that? Let's now put all of these pieces together and jump into the back of Chapter 1 and look at problem 38 in Chapter 1. And if you're lucky, that one will be assigned as a homework problem. Oh, yes, wake up if, no, I haven't yet made the homework up, so let's see what happens. Here is, and I'm hopefully have enough, I don't have the book with me, but I'm hoping I have it written down well enough. On an exam, if I fail to write these little dots, or if I don't get quite all the way to the box or a line, you can probably infer that it is a connection. Some of the currents that are labeled, I think, are consistent with the labels on these boxes. These boxes indicate R's or sources. Let's say that's I sub A, I sub F, I sub D, I sub B, I sub C, I sub G, I sub E, and I sub H. The particular problem says that we are given I sub A is (2 amps), I sub B is 3 amps, I sub D is minus 5 amps, and I sub H is 4 amps. And we need to find the other I sub K's that we haven't been given. How are we going to do this? Hopefully it's all on one page for you. We were given I sub A. What else were we given? Is that what you wanted?
Yeah.
Can you see that still? Just reduced by 3/4. We were given I sub A, I sub B, I sub D, and I sub H. Suppose we now say, well, for our solution, let's just start identifying unique nodes. And once we have nodes defined, we can apply KCL. And hopefully that process will yield some equations so that we can solve for the unknown I sub k's. That's the process that we will try to follow. If I go back and identify some nodes, is that a node? That's okay for a node. This is actually just one node, isn't it? Let's call that 2. Here's another node. We'll call that 3, and that node actually can be all this. I hope that's clear. Another node is here. Another node is here. And have I missed any nodes? Hopefully not. Let's start with node number 1. What do we know from KCL? How many nodes or how many currents are associated with node 1? We have 3. And those were given to us already drawn. We didn't get to select those. Those are just given to us, and we have to live with what we're given. In your analysis, they may not even be drawn. You'll have to draw those and just live with what you've drawn. In this case, if we say, oh, the sum of the currents going into the node has to equal 0, I sub A and I sub D are both going in, I sub F is going out. That will be a minus sign on I sub F, but I sub A and I sub D are both going to be positive. So that we now, from node 1, KCL at node 1 says that we have I sub A plus I sub D minus I sub F is equal to 0. Or we were already given I sub D and I sub A, and we just have one unknown in that equation. We can solve for that unknown, which is I sub F, and that's equal to I sub A plus I sub D. I sub A is 2. I sub D is a minus 5, which means I sub F is minus 3. What does that mean physically? If I sub F is minus 3. It's actually going into the node, isn't it? You could, if you wanted to, redraw that, but that's just going to confuse things for now. I would just say, okay, I sub F is minus 3. That just means that it's going in the opposite direction as it's drawn. Let's do KCL at node 3. I don't like node 2. It looks too complicated. KCL at 3. We have one current going into 3, 2 going out. I sub B minus I sub A minus I sub C. Is that correct? Or we have, well, I could write it the other way. I could say the sum of the currents out equals 0. If I do that, I sub A was going out of node 3. I sub B was going in, so it's now negative. I sub C was going out, and that's what I said was positive in this particular way that I'm writing. And now I have I sub A minus I sub B plus I sub C equals 0. Or I could have done the other and just multiplied both sides by minus 1, and it'd give me the same relationship. I already know, I think, do I sub A and I sub B. Let me solve for I sub C. I sub C is now I sub B minus I sub A. I sub B was 3. I sub A was 2. I sub C is then 1 amp. And if you wanted things to be positive currents, then you guessed right, or the book gave you the right direction for I sub C. Let's do KCL at node 5. At node 5, I'm going to cheat and not scroll back. I'm getting dizzy watching it scroll. I have my sheet in front of me. You have your notes in front of you. I'm assuming then that for KCL at node 5, let's say that the sum of the currents in is what we'll treat as positive. I sub F flows into node 5. I sub G flows out. That's going to be a minus. I sub H flows out. That's also a minus. But the algebraic sum of those defined currents need to be 0. What we do not know from those three is I sub G, I believe. Is that true? Since we just found I sub F in the first go-round or in the first equation, we now can say that I sub G is equal to I sub F minus I sub H. I sub F was minus 3 minus I sub H, which was given as 4. I sub G is then minus 7 amps. If we look at the bottom node and we sum the currents going in, I sub C is going into node 4, I sub E is leaving node 4, and I sub H is going into node 4. Or we have plus IC minus IE plus I sub H is equal to 0. The only one that we do not know in that collection of three currents is I sub E. I sub E is I sub C plus I sub H. I sub C is 1. I sub H is 4. And consequently, I sub E is 5 amps. Have we found all the unknown currents? Question?
Wasn't negative IH? Let's see what's going on here.
The question that was asked was, where was I sub H and how was it flowing? In the last, for node 4, I believe my convention was, let me sum the currents into node 4. The way I've drawn I sub H is into. And so all the currents going in I'm going to call positive. Any that are going out will be negative. In this case, I have IC in, IH in. Those are both positive. Going out is I sub E. I sub E will be minus. Any other questions? Did that answer your question? What we've learned is that we didn't need to write KCL at all 5 nodes, just 4 of the nodes. And so we didn't have to worry about node 2. Therefore, KCL at 2 is redundant. Or we could say we have already used 4 independent equations. To find the 4 unknown currents. Questions on problem 38? Yes. Yes. I'm sorry?
On node 1 and 3?
Yes.
When you set it up, node 1, you had current A going in as positive, but on node 3, you have current going out as positive.
Okay, good question. The question was, if I can stumble back down to the front of the class. I have to wake up too occasionally. I used a different convention in those two relationships. The question was, why did you have, I think, I1, now I have to remind myself by looking at the diagram, and I don't want to scroll. In one of the relationships for node 1, I called I sub A positive. And then when I looked at node 3, I called I sub A negative, positive. Is that okay? So I called I sub A positive when it was going into the node for node 1, and I called I sub A positive when it was going out of node 3. Is that okay? It's okay as long as you don't mix them for each node that you're working on. Meaning, for node 1, I established, for whatever reason, a convention that I was going to say in is positive, out is negative. So node 1, I say IA is in, that's positive. ID is in, that's positive. And I sub F is out, that's negative. But then for node 3, I, for whatever reason, turned around and looked at it differently, and I said, now I want to change. I want to say out is positive. And so I said, okay, all the currents going out of node 3, I'm going to say are positive. So I said, okay, I sub A is positive, I sub C is positive, but I sub B is negative. And you could get what you maybe feel more comfortable with is saying, wait. Let's just always say going in is positive, and you can do that. But I was just trying to make sure that you're aware that you could do the other. Does that answer your question?
Now, given that you have negative currents, the given current, can't that change your answer, your value, because you're using currents that you solve for to go into the other nodes for the unknowns? You know, by the time you're finished, you're adding and subtracting. So you could get a 3 versus a positive 3, and then when you use that positive 3 amp later for another unknown, couldn't that change the value?
So the question is, by switching conventions halfway through the problem, is it going to mess you up? Is that what you're asking?
Mess up the other unknown.
Mess up the other unknowns. As long as you're consistent with the individual equations that you're writing, and always say I sub A, whether it's minus or plus, as long as you have assigned it, let's say in one case in is positive, and in another formula or another KCL, out is positive, as long as you don't magically change the sign of I sub A itself, you're okay. Meaning if you find I sub A to be minus 3, I sub A is always minus 3. You can't say I sub A is now 3. Well, you said in or out is plus or minus. I hope that's not what I'm saying. I'm saying that the sign is, let's say, whatever you want it to be. If I now establish a convention that in is positive, then if I sub A is going in, it would be positive in that particular writing of the equation. I tried to make it so that I had you thinking, but I don't want to confuse you. Is it clear?
Yeah.
Did I confuse everyone? But I did it somewhat intentionally so that you would have to think about what I was doing. In one case I said it's in is positive, and in the other case I said out is positive. But as long as I don't change halfway through the problem, or I'm sorry, halfway through a particular KCL or KVL, I'm okay. Is that making sense? All right. Let's look at another problem. Let's double 38, and that's 76, isn't it? I don't normally just double a problem and say, let's do the next one. In terms of frequencies, what happens when you double a frequency? You go up an octave. I was looking up what is the frequency for middle C. Whew, that opened up a whole Pandora's box. But the A above middle C is 440 hertz. And depending on how you backed your way back to middle C, it could be in a certain range of frequencies. Oh, boy, I was completely confused. But roughly one person thought middle C was 264.298 hertz. That was one of your homework assignments, wasn't it? All right. Just don't ask me to sing. I'm sorry? I'm not even going to repeat that question. The question was, we get to hand in homework at the end of class, and yes, that is the policy. But that was just a, how do I want to say it? An ungraded homework assignment. How's that? Can it be for extra credit? I'm anticipating your questions. Find I sub s. Have I given you enough information? Just as a review, what is I sub s? It's a source, and it's a current source, isn't it? And we're trying to find the value of that current source. What's in between, or what's the next vertical element as we move from left to right, as we go to the right on from I sub s? That's also a current source, isn't it? But it's dependent. And if this was an exam problem and you're starting to work it and you go, okay, that's a dependent source, where's I sub x? It's only there. It needs to be somewhere else. And so you would have to have an I sub x given. I sub x is the current flowing through the 10 ohm resistor from right to left. That's how the book has defined I sub x. And they may label a voltage with an arrow. The positive, or the arrowhead on that voltage is the positive terminal, and so I would prefer to do something like plus minus. And I believe you're given in the problem statement the following information. You're told that the voltage across the 15 ohm resistor, R15, is 30 volts. Oh, maybe I gave you more than what I should have. And R15 is 15 ohms, but I had already indicated that. That's the given information, and now we need to try to back our way towards I sub s. Bless you. If we knew I sub x, then we would know I sub x over 2, correct? And if we knew the current in the rightmost branch and the current in the middle vertical branch, we could use KCL to find I sub s. So we need to find the current in the rightmost branch, and we're given a voltage and a resistor. We know that the current and voltage relationship on the resistor is going to allow us to solve for a current. Meaning, we know this is true. If I'm given a resistor, V sub R, and I sub R is here, and here's R, I know that V sub R is equal to R times I sub R. And I'm going to use that relationship to solve for, and now if it's not making sense, I just create my own quantities. Let me put a blue current in here and say, you know what, by convention, I'm going to call this I sub R15, because that's how I want to see that current through that resistor. I want it to go down through the positive terminal of resistor 15. And then I know that that 30 volts is equal to 15 times I sub R15. Does that make sense? Therefore, I sub R15 is equal to V sub R15 divided by R15. But V sub R15 was given as 30. R sub 15 was given to be 15 ohms. And we now know that I sub R15 that I've labeled, I introduced that, that's now 2 amps. Well, if I make this more explicit, suppose I say, well, I want to do a KCL at that node. I can do that. And I could say the currents out of that node need to sum to 0 if I wanted to, or I could say the currents into that node need to sum to 0. But if I now say, let me write KCL at node 1, and let me say the currents out of that node need to sum to 0. I sub x was going out of node 1. And the way that I had defined I sub R15, that was also going out, and those are going to sum to 0. Question? Where is node 1? I just put it in there, and then I scrolled down and basically had it disappear. Node 1 is between the 10 ohm resistor and the 15 ohm resistor. I'm not sure I repeated the question, but that's node 1. The question was, where is node 1? Is that better? Yes, I scrolled down after I drew it on there, and if you were thinking or looking somewhere else, it wouldn't be clear where node 1 was. Now that I'm scrolled up, because I don't want to be scrolling too many more times, let's call this node 2. The node between the 5 ohm, the 10 ohm, and the dependent current source. And so now if I refer to that later, hopefully you know where it is. But now that I've defined node 1, what do I know about I sub x and I sub R15? They're opposite, aren't they? Meaning if I sub R15 is 2 amps, I sub x must be minus 2. And if I now do KCL at 2, I have my source current I sub S going in. I have I sub X from the right going in to node 2. And I have going out down vertically minus I sub X over 2. Those three currents algebraically need to sum to 0. And I just found I sub X, which is going to allow me to solve for I sub S. I sub S, if I put the two I sub X terms on the other side, I have a minus I sub X over 2. I sub X was minus 2, or I sub S is 1 amp. Yes, question?
I had a question when you found I sub R15.
Yes?
You knew to draw it that way, but let's say that you drew it the opposite way. How would you make the voltage negative, or how do you know?
Okay, so the question was, going back a little bit here, I intuitively knew, well, not intuitively, but with experience, I realized I wanted to draw I sub R15 vertically down with the arrow going down. And the reason I did that is because I know that if I draw it vertically down, it's going into the positive terminal of that resistor, which gives me the convention, the passive sign convention that we're using. But if I would have, if it was 2 a.m. and I was working this problem and I was tired and I drew it going up, I would say, okay, there's I sub R15. That's actually the same as I sub X, but I want to know exactly what's going through that resistor. Then you would say, what's the voltage drop across that 15 ohm resistor? You now have it going into the negative terminal of your resistor. And so you now have, you could say, minus V sub R15 is equal to 15 times I sub R15. Or you have I sub R15 is minus 30 over 15, or it's minus 2. Is that making any sense? Let me draw that picture. The question was, what if instead of, to begin with, here's this 15 ohm resistor, and we're told that this is 30 volts, but what if I would have said this is I sub R15? Then I know that the way this is minus 30 volts is equal to 15 times I sub R15, the way that that's drawn. And if I now solve for I sub R15, that's minus 30 over 15. Maybe I should have called that something else. Let me call that I sub hat so that you don't confuse it with what I've already defined. This is now minus 2 amps. And I sub R15 hat is identical to I sub X, and that's minus 2 amps. Is that making any sense? Everyone is restless. And we still have a minute to go. Your assignment, chapters 1 and 2, correct? That you need to be reading. We've now covered or completed chapter 1. We'll begin chapter 2 on Tuesday. Have a good weekend. I'll see you in a few days.